Looking at that picture, it's very nice because it's all, apparently it's very warm in those countries, and we in our country, we need natural gas for heating our houses and also for cooking our dinner. Resume slideshow, that's very interesting. So, okay. The problem is there is a huge variation in composition and the quality of natural gas in our natural gas grids. And we can measure the gas quality with the Wobbe index, which is a measure for the amount of megajoules inside a cubic meter. So why is this Wobbe index fluctuating? There are several causes. One cause is the blending of natural gas from different countries. So for instance, from the Netherlands, from Russia. So maybe that problem will be solved soon. If we don't get any gas from Russia anymore, from Norway, etc. Furthermore, we want to add maybe biomethane, biogas. And of course, there are periodical variations in both gas types. How can I get rid of this? No. Okay, so the problem is already there. For instance, these are the current variations in gas quality in the German gas grid. So here we see the Wobbe index in megajoule per cubic meter. And I've indicated the lowest value and the highest value. So which means your heating appliance at home or the appliance where you cook your dinner or your boiler could have energy content. The minimum value is about 42. And the maximum value is about 55. So if you have that within 1 hour or within several minutes, the flame maybe is distinguished, or you have a very big flame, so you get burnt. So fortunately, there are some properties of the gas mixture, like the density and the viscosity, and we can correlate them more or less to the Wobbe index. So if you are capable of measuring one or more of these parameters, we should be able to also measure the Wobbe index. Of course, it's called monitoring the gas quality. Of course, there is already equipment for that, like the normal Wobbe index meter. But this is a very big device. It's 2 meters high and 1 meter wide and half a meter thick. And also the gas chromatograph. And all of these systems, it's nice, and it will give you a very accurate, at ppm level, value of the Wobbe index. However, it's bulky equipment. It's expensive, of the order of, it can go up to 70,000 euros. It has a large gas consumption, and the gas chromatograph is slow, typically of the order of minutes, maybe of hours. A real Wobbe index meter is fast. It's about 1 second. Response time 1 to 5 seconds. So requirements. So the accuracy is a little bit moderate, 5%. However, we want it to have a relatively small size, low cost, fast response, have a really low gas consumption, and most important, provide real-time information about the composition. So we want to have a gas monitor, and we want to apply it at any point of use and any point of produce, which is a lot. So this is one example of the smart gas grid. This is your normal gas grid. I don't know if this is normal in the Netherlands. I think also in Germany. I don't know if you use, for instance, here in Spain, a lot of natural gas. You have the central gas supply by the national gas grid, and from there it is distributed to the big industrial users and to the homes. And here you have some biogas, biomethane is fed into the gas grid. So at all these places, we need reliable, small and cost-effective equipment to measure, to monitor the gas quality. So lots of market opportunities. So how are we able to measure this gas quality? We do that with our multiparameter flow measurement system. And so it is under continuous flow. So the flow goes into the system like this and goes like that, and here it leaves the system again. And while flowing, we measure at the same time the density with a density sensor, the mass flow with a Coriolis flow sensor, the differential pressure over the line with a differential pressure sensor, and again the mass flow with a thermal flow sensor. And this we can put into a model, and with this model we can determine the gas composition. So how do we do it? This model is divided into two sections. The first section, we derive the parameters of the gas mixture from the sensors. I will explain. So as I said, from the Coriolis sensor we get the mass flow. From the thermal sensor we get the mass flow, but together with the heat capacity. So when we compare these two signals, we get also the heat capacity of the gas mixture. Of course, the density sensor provides us with the density of the gas mixture, and then the combination of density, mass flow, and the output signal of the pressure sensor provides us with the viscosity of the mixture. So that's the first stage. Now we have derived all the parameters of the mixture, and now we can go into the system model, and there we can derive the composition or the Wobbe index. So in this current system, we are limited to compositions, gas mixtures consisting of 4 different gases. So here you see a matrix, and with this matrix we are able to find the composition via n equations with n unknowns. So in this time it's 4. So then we get, for instance, the percentage of methane in biogas. And the other way is how we determine the Wobbe index. It's, for instance, via correlation with the viscosity of the gas mixture. So we can determine that via correlation, like this way, the second method. So why is it necessary to measure more than one parameter? Because there are also systems existing which determine the Wobbe index only from the viscosity. Okay, that's interesting, and you could do that. However, for instance, if you have a gas mixture with not only methane, but also with nitrogen gas and carbon dioxide, so both nitrogen and carbon dioxide, they do not contribute to the Wobbe index. However, they will effectively have a different viscosity. So, therefore, if you only measure the viscosity and try to derive the Wobbe index from that, and you have a mixture of also nitrogen and carbon dioxide inside, you have this bands of uncertainty. So the top one and the below one. So it's a huge uncertainty. However, the density is still a distinguishable parameter. So if we add the density, we correct this value for the density, we can narrow the band of uncertainty to this value. So therefore, multiparameters will increase the accuracy and will diminish the uncertainty of your measurement. So we built the system. So we just took equipment that is there, so a Coriolis instrument, thermal flow sensor, a density sensor, and a differential pressure sensor here. We connected it all together. This is the first version. We also made it into a nice little housing, and there we performed tests. Of course, you have to start easy. So we started only with a binary mixture, so it was methane gas and carbon dioxide. And we varied the amount of methane gas in the system. So we started at 100% carbon dioxide, and we gradually increased the methane content until approximately 100%. And here you show the results. So the system provided accurate information of the composition of this binary mixture with an accuracy of 1%. Okay, easy, only 2 gases. Next, we will apply 3 different gases. So in this mixture, we applied methane gas, nitrogen, and propane gas. And you see here, this was applied, and you see the measured values are in close correspondence with the applied values, and the results were within 5%. And from the overall gas mixture parameters, we were able to derive the Wobbe index, and this was also done within 5%. So another ternary gas mixture so this is more typical for biogas, where you have methane and carbon dioxide and nitrogen, And again, the results between modeling and measurement results are within 5%. So this is the composition of the gas. And this is the Wobbe index, again, within 5% of the model. And of course, the proof of the pudding is in the eating. So again, we went to this supplier of the German gas grid who has in stock these 13 different natural gases, and they are all fed into the German gas grid. And with our system, we did a measurement. So here you see this red dots are these 13. We measured 11, so these 11 different gases. And the Wobbe index we obtained from the density and from the heat capacity, again within an accuracy of 5%. So we were very happy because we didn't tune anything with the system. We just built it and did the measurements. So in conclusion, we designed and realized a compact multi-parameter flow measurement system which consisted of a density meter, Coriolis flow meter, thermal flow meter and a pressure sensor, all off the shelf. And we measured composition of binary and ternary gas mixtures with an accuracy within 5%. And the same goes for the Wobbe index of 11 natural gas compositions, also within 5%. And in the future we will improve the system further. So thank you for your attention.